I haven't had my microphone on this whole goddamn time. Do I dub over everything I had, or do I start from scratch? As we prepare for coding challenge number 7, you can watch in these 20 seconds about 40 minutes of work that I did forgetting to put the microphone on in OBS. The good news is I did wrap my head around the question at hand, so let's go ahead and take a look at that now. I think I'm just going to have to zoom forward through it for 60 seconds with a voiceover. Oh, so stupid. All right. So, here we are in coding challenge 7. Let me describe what we just Benny Hilled through prior to me noticing that my OBS settings were messed up. And I've got this problem well loaded into my head, so you don't have to watch me stumble through it quite so much in real time. But what are we doing? We are building on the birthday problem from Coding Challenge 6, and in a minute we're going to build on the circle problem from Coding Challenge 6. We're just practicing using ggplot2. So let's go ahead and restart things. I've got this folder, I've got this project set up called Coding Challenge 7. In this workspace, I've got main.r and some Git stuff that we can talk about in the future, but we don't need to worry about right now. So clear everything out. I load in the tidyverse library, which gives me access to all kinds of things, including ggplot2. Somewhere in here, is it connections? It's not connections, packages. Here we go. So if I look for ggplot2, that is loaded into my workspace. I have access to those tools. And then I'm calling in my code from Coding Challenge 6. So I source into that. Now, what this line of code in here means is I am going up one folder from Coding Challenge 7. I'm going up into my 365 folder, and then I'm going down into Coding Challenge 6 and loading in main.r, which is this file here, which I have modified so that it doesn't spit anything out at the end, because I just want to load in these functions. This isn't the only way to access other code you've written before, but since I keep my code for this class relatively well organized, not perfect, but relatively well organized, it'll do the trick. So I'm loading in this code so that now I have access to those functions, hypothetically. There we go. I have access to these functions. Now, what are these functions? If you haven't gone through this stuff already, in Module 6, I went through Coding Challenge 6, and we will have talked through a lot of the details there. But what we've got in here, I'll do a very quick walkthrough of this. I did a much more elaborate walkthrough before, which I don't know if I'm going to, maybe I'll make this a really high frame rate flashback video, and you could go through frame by frame and see everything I did and try and figure it out. But what I've got is a function that creates a sample of random birthdays, a function that sees if there are at least 2 shared birthdays within that sample. There might be more. We could make this more elaborate. In the past I have. I'm not going to do it here. If you search through my old replets, you might find some code that does a more elaborate take on this problem. So we can make a random birthday group, a group of random birthdays. We can check if that random group includes any overlap, which in this case I'm doing by seeing, are there, if of the unique birthdays in that list, how many unique birthdays do we have, and how does that compare to how many birthdays we have, including double counts? So this allows us to do our basic check on our birthday problem question. We got a group of people. Do we have any shared birthdays? Nice and easy. Then we can repeat that many times with many samples. So how are we going to do that? We're going to create a bunch of groups. So we're going to repeat our group size some number of repetitions. So repeat 23 10 times. And then we're going to apply birthday sample with a group size of 23 or 50 or 100 or whatever we put in here. I elaborated on this at length a half hour ago, but some group sizes we don't even need to check. If we have a group size of 1, it's impossible for there to be a shared birthday because there isn't anyone to share it with. If we have a group size of 1,000, we have a guaranteed overlap because there are not 1,000 unique birthdays in a year. So we're creating a whole bunch of groups of birthdays, and then we're checking all of those. So we're going to end up with a list of vectors of birthdays. Then we're going to end up with a vector of true false values. Was the vector from our list a match all the way down for 10 repetitions, right? Or however many times we repeat. And then we can estimate the probability by adding up all the trues and dividing by the number of repetitions. So if we get 7 matches, 7 divided by 10 gives us an estimated probability of 0.7, right? Or 70%. All right. So we've loaded all that in. I was looking at the question of what group sizes do we want to check? Well, 2 to 366. It's very unlikely that we have exactly 366 unique birthdays in one sample, but technically it's possible. How many samples are we going to check? 1,000 is where we're going to start. We can add some zeros once it looks better. But when it was at, I forget what value, back here when we were checking 1,000,000 values, it took 23 seconds, which is long. 10,000 is going to be long when we're checking 360 different birthdays, group sizes. 1,000 was pretty quick, so we're going to start with 1,000 and we'll make it more elaborate afterwards. Cool. So we've got a group size. We've got samples to check. Now what we want to do is we want to go over each of these unique birthdays and check 1,000 times to see how many matches we get and get the estimated probability from those 1,000 random samples. So we're going to lapply over the group sizes. What this is going to do is going to give us, a list back with the output of many samples. But many samples takes 2 inputs, so it's just going to be a little bit easier for us to wrap that up in what we call an anonymous function. So one way we could do this, a more direct way would be, let's say, function 2 is a function that takes, let's say, x as a variable, and it returns the results of function 1 with x and y equals sample size, right? Something like that. Here we've named the function 2, and then we could just apply that in here. We could call this function 2 and do it like that. And actually, putting it like that, it actually looks kind of readable, a little bit better than the anonymous function. But let me show you what the anonymous function is. In this case, we are creating something called function that takes some input x, which is going to be our group size. So x is going to get plugged in as the group size when we are repeating the function many samples, where the repetitions is going to be just this sample size that we're defining in our script. So we say our group sizes is going to be this set of numbers. Our sample size is going to be this. And our data frame is going to be the result of running this lapply. And you can see with 1,000 samples, right, 1,000 groups of 1, 1,000 groups of 2, 1,000 groups of 3, took a little while, took a few seconds. Not a huge amount, but something. Now, if we did system.time, and we reran that code, it's going to show us exactly how long that actually takes. But while that's running, we've got our DF, which is this list, and this is basically saying for 365 unique group sizes. Right? So it took about 11 seconds to run that, and might have overwritten this, but we can see for a very small group size, we got 3 out of 1,000 matches, 8 out of 1,000, 26 out of 1,000 once we get to a group size of 2, 3, 4. So our probability is growing pretty quick, but it is still a pretty small probability. But what have we got? We've got a list of values. We've got a list of estimated probabilities. So let's go ahead and do something with that. So let's reshape sample probabilities. Let's call this estimated probabilities into a data frame. So this, we really shouldn't have even called this DF because it really wasn't a data frame. Actually, I guess we could. Let's, now, I'm going to separate this so I'm not making messy code. So let's just call this estimated probs. There we go. Ooh, and look at how the X lines up nicely there. I think that's a sign. Okay, so DF, let's go ahead and run that again. DF is going to be a data.frame where our group size is our group sizes and our estimated prob is our estimated probs. Well, let's look at that. Whoops. What happened there? Ooh, that's not what I want. Let's go ahead and make that unlist the estimated probs. Good. All right. So what was going on is I ended up with this big giant data frame with 366 column headers, which is weird. But unlisting did the trick. All right, so we've got group size, estimated probability, 0. It was 0.03, so notice our estimate, is changing pretty radically with only 1,000 samples. So let's run it for 10,000. We'll give that a little bit of time to run. Once that runs, it'll run the data frame. While that's running, let's think about our plot. So plot is going to be ggplot. Our data is going to be DF, and our aesthetics, we want our X and Y. Our X is going to be our group size, which is named group underscore size, and our Y is going to be our estimated prob. And that's really giving us the plot. So then we can say, let's give us that base plot plus geom underscore point, and we'll see what it spits out. Now, you can see the issues with efficient code start to come up with simulation because it's so easy to add a 0 to something and make some calculation take 10 times as long. So before, I think it was taking about 20 seconds, 200 seconds, so that's like 3 minutes. So any minute now, we should get a bunch of stuff going through. But while we're waiting, let's go ahead and explain what we've got. So our estimated probs is giving us this setup for DF, which is giving us something like this. Now, with 10,000 samples, we're going to have room for some more decimal places, or at least one more decimal place. Again, these are estimated probabilities, but if we were, say, running a sample size of a bajillion, we should, as our sample size grows, we should be approaching the true probability. Hey, there we go. So this is sort of a bare minimum of what I'm looking for this part of Coding Challenge 7. Now, can I make this a little bit better with geom line? Whoops. Plot plus geom line. There we go. So we've got this representation, and we can see that up to about 100, there's really not a whole lot going on. Let's try this slightly different way. So let's try plot plus geom line df equals, it's going to go that way anyways. Let's so let's filter this to group size is less than, looks like 50. It really starts to tail off. Let's say less than 75. Let's say less than or equal to 75. Geom point. Sorry, let's change that to geom line. There we go. So basically, once we've got about 75 people in the room, it's almost a foregone conclusion. Now, how does that compare to what we had on the Wikipedia page? Yeah, 75, pretty much the same deal. We've got some values here, so 75, 99.97 at 23, 50.7. So let's go ahead and look at df. So let's say this, whatever, I'm not going to filter. Scroll down, so at 23, 50.8% compared to 50.7, at 30, 70.6. So we're a little off, but we're pretty good, especially considering the fact that we didn't do any algebra. We just basically flipped a coin a whole bunch of times and set it up just so. All right, so that is that challenge. I'll leave it to you to make it more elaborate. So the next part is the circle visualization. So let's call this the birthday plot. And let's go ahead and just keep this all together in one thing. So when we do birthday plot, it spits out that visualization. All right, I'm going to play this at 4 times speed because it doesn't need to take this long. The short version is, in order to save our work, we need to save it as an image file. So using the PNG function, we can save it with a file name, right? That sets things up. Then we put in the actual thing we're trying to save, in this case, birthday plot, and then dev.auth, open close parentheses. That'll do the trick. We don't need to know more. We don't need to know the detail that I'm talking about right now. All right. Now that we've saved our work, let's go back to the circle visualization. And just for simplicity's sake, just for simplicity's sake, clear everything out. We don't really need to reload in the tidyverse because that will have been done. And then we're going to load in circle.r, which doesn't exist. Oh, circle.r with a lowercase r. Naming convention. You can see, if you look in my 365 folder, coding challenge, space, all caps, all title caps. Coding challenge 2, capital C, underscore, lowercase c, underscore 2. I'm not consistent, and that's annoying. The stakes are low for me because I'm almost always coding alone. But if you're working on a team, you want to be consistent with this sort of stuff to avoid these little mistakes like what I just did here. It's an inefficiency, right? It's a little bit of drag that slows down my ability to get stuff from my brain onto the screen. In any case, we load in that stuff, and it is taking a while because it's estimating this stuff because I've got all that stuff. Let's go ahead and stop that. All right, so estimate pi is a function, estimate n, doing that. Let's go ahead and make sense of what this code is before we just blindly load it in. So we are, in this case, putting 1,000 random dots on a random square from -1 to +1 and -1 to +1. The points we're putting into this data frame. So we got these random x coordinates, these random y coordinates, right? So we're making 1,000 random x coordinates, 1,000 random y coordinates. They're just mashing together. They were independently assigned. So this is effectively random xy coordinates. Cool. Then using these points, we ask how far away from the origin is a particular point. So if we randomly look at a point with the x coordinates positive 0.05 and the y coordinate negative 0.05, if here's the middle, we're going positive 0.05 over here, negative 0.05, we're going down here, and that looks like it's inside of this circle that you can see on your screen here. So all we're saying there is that this point we've decided on, we've randomly assigned, we've estimated the radius, and it's less than 1, right? Which is what we're getting here, right? So we've got how far from the origin is it, and is that distance less than 1? And then we're going to have a bunch of these dots. Some are inside the circle, some are outside the circle, and estimating that ratio is going to be how we find pi. There are many ways to do it, but this is the way that I did it when I wrote this code a couple weeks ago. So just to drive this point home, let's say n equals 1,000. Let's run some of this code. So here's our x coordinates, our y coordinates, here's our points and the radius. So our x coordinates, let's look at environment. So our x coordinates, we got all these random numbers. Our y coordinates, we got all these random numbers. Ignore this. This is from that stuff. That shouldn't be there, but whatever. Oh yeah, we sourced it. I just loaded that. Actually, okay, so this is fine. This is good. We can see what the results are when we run the code. But what we've got at this point, if we look at points, if we look at the head of points, we got an x coordinate, a y coordinate, and a radius. When it's a little further out, that radius is more than 1, and that one is not in the circle. If we take the sum of the points in circle, we add up all those trues, we've got 766 out of 1,000 are in that circle. So divide that by 1,000, and we've got 0.766, which is not a good estimate of pi, but 4 times that, well, that's actually a little bit closer. Why is it times 4? It's because this stuff we're doing. It's, well, sorry, why is it 4? It's because if we're making a square that goes from 0, 0 to +1 to -1, up and down, we've got 4 unit squares that we're dealing with. We're finding the ratio, but effectively we're finding the ratio within a quadrant. And then we multiply that estimate out. We've kind of got this weird overlap. Why? I don't know. It just doesn't, it's not sitting in my head right now. And I've been working on this for 1 hour and 6 minutes. Ask YouTube. YouTube has a good answer for you. And I'll bet there's some really cool visualizations. And you'll improve your algorithm to be something a little bit more interesting than, whatever it pushes you to by default. So estimate pi gives us an estimate. And here are some estimates we've run. So 1e to the 4, this is just 10,000. 1e to the 5 is 100,000, and so on. So if our sample size is kind of big, or actually quite big, our estimates go from 3.1488, sometimes a little off. 3.1415, I think, is the true value. 3.14159. We're pretty close when we do this 1,000,000 times. How close? We're, the third decimal place in, I guess that would round to 3.142. So yeah, we basically got a 3-digit estimate running it with that. If we do, I'm not going to run that. I was going to run system.time. Actually, I will do it with estimate pi 1e to the 3 with 1,000. 1e to the 4, 1e to the 5. Okay, that's not too bad. So x1, that took 1/10 of a second for us to get that. We have loaded in a way to do this. Let's comment those out. Estimate n. This was asking how large an n do I need to figure out a good estimate. And what did I have for t? Did it run t? It didn't. All right, well, that's doing that. Maybe we get an estimate for what is a good number of repetitions to do. All right, so we want to visualize this. So what can we do? Well, if we're returning the whole, that's returning the data frame. Here we're returning an estimate of pi. So, you know, let's go ahead and just take this code, paste it into here, and let's not use this version. So let's call this function makeDF. Whoops. And let's have it return. Actually, you know what? I will keep that pi estimate. So I'm going to have it return a list of piest equals piest and df equals points. We will return that. And then let's just say df is make df for 10,000. So we're going to get 10,000 random points eventually. What will we do with those? Well, our plot can be ggplot. Our data frame will be df. Our aesthetics are going to be x chords and y chords. And let's say color equals insert. And let's say alpha equals, let's say alpha equals radius plus geom point. And we'll run plot. All right, so I'm going to skip this. Define make df, run our df, define our plot. We get an error. Let's run our plot. That didn't work. Good. Error in fortify. Must be an object coercible by fortify. Let's look at the head. Oh, I know what went wrong. Okay. This should be df $df. Slightly annoying, but let me explain in a second. Fix the following: x equals y equals. So df is a list. All right. I'm gonna let that go to voicemail. Oh, yeah. So structure of df. We've got two things. We had our pi estimate, which was 3.18, which is not great. And then we've got a data frame. 10,000 observations of 4 variables, x, y, radius, and insert. Okay, so let's go back to here. So let's call that df list, and we'll say df equals df. Did I call it df? I did call it df. This is slightly annoying. Okay, so df list is that. Now if I go df list df, norc, df dollar df. There we go. All right. Okay, so df will be that df. We run that plot, and then let's look at the plot. Oh, you turd. Not working, and I gotta run pretty soon. The df gm point. That's good. Let's put that on a separate line just so it's a little easier to see. And on a separate line so it's a little easier to see. Oh, that's not going to work. Now let's try it. There we go. Hey, all right. So what have I got here? We're taking this data frame that we pulled out of this list. All right, so I took that old code I had, I modified it so that it kept that points data frame, which is really the valuable thing. So here are those points that I made up, right? These 10,000 points between -1 and +1 on X, and -1 and +1 on Y. Their radius, the further out they are, the darker they are, the closer they are to 0, the lighter they are. Right? So that's an arbitrary decision, but just to make the point. And their color is either red if they're outside the circle or green if they're inside the circle. So my estimate of pi, which was not great, but it was an estimate, was based on counting all of these green dots and comparing them to the number of total dots. That ratio was about 70%, right? So now if you think of, let's just kind of visualize one quadrant here. If 70% of your dots are in here and the total area is 1, right? 1 times 1, then that's giving you something. But we want 2 times 2. Whoops. Don't need to save that picture. We need 2 times 2. I guess I could save that picture. PNG. What are we going to call this? CirclePlot.png. I'll keep the defaults and dev.off. There we go. And now when I go to Files for Coding Challenge 7, PNT doesn't exist. Let's try PNG. There we go. Now I've got my circle plot. Good. All right. That was a long walk. I'm going to have to do a bunch of editing to make sense of this, but we are done for right now. All right. As usual, if you have questions, let me know in the usual places, and I'll talk to you in the future.